In this section, we'll explore the event horizon, one of the most fascinating aspects of black holes. The event horizon is the boundary around a black hole beyond which nothing can escape, not even light. It's not a physical surface you could touch, but rather a mathematical boundary in spacetime. The event horizon marks the point where the gravitational pull becomes so intense that the escape velocity exceeds the speed of light. Outside the event horizon, light can still escape from the black hole's gravitational pull. At the event horizon itself, light can orbit the black hole in what's called the photon sphere. But inside the event horizon, all paths lead inevitably to the singularity at the center. The event horizon exists because of how black holes curve the fabric of spacetime. To summarize, the event horizon is the boundary around a black hole beyond which nothing can escape, not even light. It marks the point where escape velocity equals the speed of light, creating a one-way boundary in spacetime. This boundary isn't a physical surface you could touch, but rather a mathematical point of no return defined by gravity's effects on spacetime.
When matter crosses the event horizon of a black hole, we observe two very different perspectives of the same physical event. Let's first establish our two viewpoints: an outside observer watching from a safe distance, and an observer or object falling toward the black hole. From the outside observer's perspective, as matter approaches the event horizon, it appears to slow down dramatically due to extreme gravitational time dilation. As the matter gets extremely close to the horizon, it appears to freeze in time from our perspective. Light from the object becomes increasingly redshifted, and it seems to never quite cross the horizon. However, from the perspective of the falling observer, the experience is entirely different. They would cross the event horizon without noticing any special boundary. This difference in perspectives comes from the extreme curvature of space-time near the event horizon. For the falling observer, proper time continues normally, and they pass through what appears to be just empty space. Meanwhile, from our outside perspective, the time dilation becomes so extreme at the horizon that we would have to wait an infinite amount of time to actually see the object cross. This fascinating contrast between the two perspectives is a direct consequence of Einstein's theory of general relativity and the extreme warping of spacetime near black holes.
Let's explore the extreme time dilation effects that occur near the event horizon of a black hole. Time dilation is a consequence of Einstein's general relativity, where gravity affects the passage of time. As an observer approaches a black hole, time for them continues to flow normally according to their own clock. However, when viewed from a distance, the infalling observer's time appears to slow down dramatically. As the observer gets closer to the event horizon, time dilation becomes more extreme. From the perspective of the infalling observer, time in the outside universe appears to speed up dramatically. As the observer crosses the event horizon, they could potentially witness billions of years pass in the outside universe in what seems like mere moments to them. This extreme time dilation is a fundamental property of spacetime near black holes. The closer you get to the event horizon, the more pronounced the effect becomes. At the event horizon itself, from an external observer's perspective, time appears to stop completely. However, the infalling observer experiences nothing unusual as they cross this boundary. This profound difference in the experience of time is one of the most fascinating aspects of black hole physics, highlighting the extreme warping of spacetime in these cosmic objects. The event horizon of a black hole marks a profound boundary in spacetime. Outside the event horizon, objects have multiple possible paths through spacetime. But once inside the event horizon, the rules change dramatically. All possible paths through spacetime lead to the singularity at the center. This happens because of a fundamental reordering of spacetime geometry. Outside the black hole, time points upward in our diagrams, and space extends outward. But inside the event horizon, the radial direction toward the center essentially becomes a time-like direction. This means that moving toward the singularity becomes as inevitable as moving forward through time in the normal universe. Just as you cannot move backward in time in normal space, once inside the event horizon, you cannot move away from the singularity. This can be understood mathematically through the Schwarzschild metric, which describes spacetime around a black hole. At the event horizon, where r equals 2m, the metric components change sign. Inside the horizon, the radial coordinate r effectively becomes timelike, and movement towards smaller r values becomes inevitable. This fundamental reordering of spacetime geometry is what gives the event horizon its one-way nature. Once inside, all possible futures terminate at the singularity. This unavoidable journey toward the singularity leads to another fascinating phenomenon known as spaghettification. The process of spaghettification occurs as an object falls into a black hole. Tidal forces occur because gravity follows the inverse square law. The force is stronger on the parts of the object closer to the black hole. Mathematically, the tidal force difference increases as the cube of decreasing distance to the center of mass. This creates an extremely steep gradient near the singularity. As the object falls toward the event horizon, it begins to experience these tidal forces. The side closer to the black hole feels a stronger pull. As it gets closer to the event horizon, the object begins to stretch vertically and compress horizontally. This deformation is still relatively mild at this distance. Inside the event horizon, the tidal forces become extreme. The object now experiences intense vertical stretching and horizontal compression. This is the full spaghettification process in action. The spaghettification process becomes most extreme near the singularity, where the tidal forces approach infinity. Any physical object would be stretched into an infinitesimally thin stream of particles. The difference in gravitational force between the top and bottom of the object becomes so extreme that no physical material could withstand it. This is why spaghettification would destroy any object falling into a black hole, even before it reaches the singularity. As we venture deeper into a black hole beyond the event horizon, we encounter perhaps the most mysterious aspect of these cosmic objects, the singularity. At the very center of a black hole lies what physics predicts to be a singularity, a point of infinite density and zero volume. At this point, spacetime curvature becomes infinite. This is not simply an extreme condition. It represents a mathematical breakdown in our current understanding of physics. Here, general relativity, which describes gravity as curved spacetime, predicts its own failure. The theory produces infinite values, signaling that our current understanding of physics is incomplete at this extreme. Many physicists believe that at the singularity, quantum gravity effects likely become dominant. Quantum mechanics, which governs the behavior of very small objects, must somehow merge with gravity at this extreme point. Unfortunately, we don't yet have a complete theory of quantum gravity to describe exactly what happens at the singularity. Various approaches like string theory and loop quantum gravity provide potential frameworks, but none have been conclusively proven. The true nature of the singularity remains one of the greatest unsolved mysteries in modern physics. Understanding it may require a fundamental reimagining of space, time, and the laws of nature themselves. Einstein's theory of general relativity provides our most accurate description of black holes and what occurs inside the event horizon. At its core, general relativity describes how mass and energy curve the fabric of spacetime. When a massive object is present, it creates a depression in this fabric, similar to how a bowling ball would create a depression on a trampoline. This relationship is elegantly captured in Einstein's field equations, which mathematically describe how matter and energy determine the geometry of spacetime. The left side of the equation represents the curvature of spacetime, while the right side represents the distribution of matter and energy. In essence, these equations tell us that matter tells space how to curve, and space tells matter how to move. In the case of a black hole, the mass is so concentrated that it creates extreme curvature in spacetime. This curvature becomes so severe that beyond the event horizon, all paths lead inevitably toward the center. However, one of the most profound aspects of general relativity is that it predicts its own limitations. At the center of a black hole, the theory predicts a singularity where all known laws of physics break down. At the singularity, general relativity predicts infinite density and infinite spacetime curvature. These infinities are mathematical signs that the theory is no longer applicable. This self-predicted breakdown suggests that general relativity is not the complete picture. To fully understand what happens at the singularity, we would need a theory that combines general relativity with quantum mechanics, a quantum theory of gravity. While general relativity gives us our best description of black holes, it also points to its own limitations and the need for deeper theories in extreme conditions. Unlike static Schwarzschild black holes, rotating black holes are described by the Kerr metric, named after mathematician Roy Kerr. These black holes possess angular momentum, which significantly alters their spacetime geometry. The mathematical solutions for rotating black holes predict a second boundary inside the event horizon, known as the inner horizon or Cauchy horizon. This is a unique feature not present in non-rotating black holes. The mathematical solutions for rotating black holes predict a second boundary inside the event horizon, known as the inner horizon or Cauchy horizon. This is a unique feature not present in non-rotating black holes. The region between the event horizon and inner horizon creates a domain where causality becomes even stranger. Theoretical models suggest that inside the inner horizon, there might exist paths that allow objects to avoid the central singularity. The mathematical solutions for rotating black holes predict a second boundary inside the event horizon, known as the inner horizon or Cauchy horizon. This is a unique feature not present in non-rotating black holes. The region between the event horizon and inner horizon creates a domain where causality becomes even stranger. Theoretical models suggest that inside the inner horizon, there might exist paths that allow objects to avoid the central singularity. Despite these intriguing theoretical possibilities, most physicists believe the inner horizon cannot physically exist. The inner horizon would experience catastrophic instabilities due to infinite blue shift of radiation and a phenomenon known as mass inflation. To summarize, while the mathematics of rotating black holes predicts an inner horizon with fascinating properties, the extreme conditions there would likely destabilize it, making its actual existence physically impossible. Quantum fluctuations represent the inherent uncertainty in quantum fields, where virtual particles continuously appear and disappear from the vacuum. In normal space, these fluctuations follow the uncertainty principle, where energy can be borrowed from the vacuum for very brief periods of time. Inside the event horizon, however, extreme gravity radically changes how these quantum fluctuations behave. The tremendous spacetime curvature near a black hole's singularity amplifies quantum fluctuations, potentially creating exotic quantum effects not seen anywhere else in the universe. Virtual particles may have dramatically extended lifetimes. Pair production could be enhanced, and entirely new quantum gravity phenomena might emerge. These quantum fluctuations may play a crucial role in resolving the information paradox and could help us understand how quantum mechanics and general relativity might be unified at extreme energy scales. The holographic principle is one of the most profound and counterintuitive ideas in modern physics. It suggests that all the information contained in a three-dimensional volume of space can be encoded on its two-dimensional boundary. To understand this concept, imagine a three-dimensional object like this cube. Now imagine a two-dimensional surface, like a screen. According to the holographic principle, all the information contained in our cube can be encoded on the surface of this two-dimensional screen. This principle has profound implications for black holes. When an object falls into a black hole, it appears to disappear beyond the event horizon. However, the holographic principle suggests that all the information about what falls into the black hole isn't truly lost. Instead, it's encoded on the two-dimensional event horizon, much like our hologram example. The event horizon acts as a storage medium for all the information about everything that has fallen in. This principle offers a potential resolution to the black hole information paradox by suggesting that information isn't truly lost when it falls into a black hole. It's preserved in a different form. The holographic principle thus represents a fundamental shift in how we understand information, dimensionality, and the nature of reality itself. Some theoretical models suggest that black holes might connect to other regions of spacetime through what physicists call wormholes. In 1935, Albert Einstein and Nathan Rosen proposed a theoretical solution to Einstein's field equations that suggested the possibility of bridges connecting different points in spacetime. These Einstein-Rosen bridges theoretically connect two separate regions of spacetime, potentially allowing a connection between a black hole and what would appear to be a white hole in another region of the universe. In theory, matter entering a black hole might emerge from a white hole, which acts like a time-reversed black hole, expelling matter and energy. However, this remains highly speculative. Wormholes face significant physical challenges that may prevent them from existing in reality. For instance, maintaining a stable wormhole would require exotic matter with negative energy density to hold open the throat against gravitational collapse. Nevertheless, several theoretical models derived from Einstein's field equations do allow for the mathematical possibility of wormholes. The Morris-Thorne metric provides a framework for traversable wormholes, though it requires conditions that may not be physically possible. For now, Einstein-Rosen bridges remain a fascinating possibility for what might exist beyond the event horizon, but they're still firmly in the realm of theoretical physics, awaiting a deeper understanding of quantum gravity. Black holes present a unique challenge to astronomy and physics. We cannot directly observe what happens inside an event horizon because any information, including light, cannot escape once it crosses this boundary. This creates a fundamental observational limit. We can only see what happens outside the event horizon. Our understanding of what happens inside black holes comes entirely from mathematical extrapolations of physics we understand in less extreme environments. This creates a fundamental boundary in science, a divide between what we can observe empirically and what we can only theorize about mathematically. Some aspects of black hole physics may remain permanently beyond direct empirical confirmation, existing only in the realm of theoretical physics. This limitation doesn't mean we should stop trying to understand black holes, but rather that we must be mindful of the boundaries between what we know and what we infer.
Black hole complementarity presents us with one of the most fascinating paradoxes in theoretical physics. The paradox emerges from two seemingly contradictory descriptions of what happens at a black hole's event horizon. From an external observer's perspective, an object never quite crosses the event horizon due to extreme time dilation. Information appears to be encoded on the horizon itself. But from the perspective of someone falling into the black hole, the event horizon isn't special at all. They would pass through it smoothly, with nothing unusual happening at that specific moment. These descriptions seem fundamentally contradictory. How can information be both trapped at the horizon and pass through smoothly? This is where black hole complementarity comes in. Proposed by Leonard Susskind and Gerard Hooft, it suggests both descriptions are valid, but from different reference frames. Complementarity states that these contradictory descriptions aren't a problem because no single observer can verify both perspectives simultaneously. This is similar to quantum complementarity, where light can behave as both a wave and a particle, but never both simultaneously in the same experiment. Black hole complementarity helps resolve the information paradox without requiring a firewall, but it fundamentally challenges our classical understanding of spacetime. In essence, black hole complementarity suggests that our most basic concepts of reality may be observer-dependent in extreme gravitational scenarios.
The future of black hole physics presents some of the most exciting frontiers in theoretical physics. Understanding what truly happens inside black holes will likely require a complete theory of quantum gravity, which would unify Einstein's general relativity with quantum mechanics. Currently, physicists are pursuing several promising research directions to solve these fundamental mysteries. Holographic approaches, like the ADS-CFT correspondence, suggest that the physics inside a three-dimensional black hole can be completely described by a two-dimensional quantum theory on its boundary. Emergent spacetime theories propose that space and time themselves are not fundamental, but emerge from deeper quantum structures, similar to how temperature emerges from the motion of atoms. Advanced computational simulations allow physicists to model extreme gravity environments and test theories that would be impossible to verify experimentally. Despite these advances, the mysteries of the event horizon interior remain one of the greatest frontiers in theoretical physics. Questions about the fate of information, the nature of the singularity, and the structure of spacetime at the quantum level continue to challenge our deepest understanding of physics. Black holes don't just test the limits of physics, they challenge our deepest philosophical understanding of reality itself. At the event horizon, we encounter fundamental questions about the limits of knowledge, the nature of causality, and what we mean by physical reality. Classical physics assumes determinism that causes lead predictably to effects, but black holes challenge this foundational principle. Once events cross the event horizon, causality as we understand it may break down. The future inside a black hole may not be determined by the past in the way we expect. Laplace believed that with perfect knowledge of the present, we could predict all of the future. Black holes suggest this might be fundamentally impossible. The event horizon represents more than a physical boundary. It may be an epistemological limit to what can be known. Philosopher Immanuel Kant argued we can never know things in themselves, only their appearances. Black holes may represent a physical manifestation of this philosophical boundary. Black holes force us to reconsider what we mean by reality and existence. Philosophers have long debated the nature of reality. Realists argue that reality exists independent of observation. Anti-realists suggest reality is constructed through our perception, and quantum physics indicates reality may be probabilistic until measured. Black holes challenge all these perspectives by creating regions where observation becomes fundamentally impossible, yet physical processes must still occur. Science operates through an iterative process of observation, hypothesis, testing, and analysis. But the event horizon disrupts this process by making direct observation impossible. This raises the philosophical question: when direct observation becomes impossible, what role should theory, mathematics, and inference play in our scientific understanding? Black holes invite us to confront profound questions about the limits of human understanding. As Einstein observed, the mysterious is not just a challenge to our understanding. It's the fundamental emotion that drives both art and science forward. Perhaps black holes remind us that the universe is not just stranger than we imagine, but stranger than we can imagine.